Okay, so think about trying to create characters with AI image tools. You get these amazing pictures sometimes, but getting them to be consistent.
Yeah, that's the real headache.
Exactly.
Yeah.
Like the same character, different scenes, different styles. If you're doing storytelling, comics, games, that kind of reliable control, it's felt, well, kind of out of reach.
It really has. And the demand for that level of precision, it's just going up and up right now,
Oh, yeah.
especially in creative fields.
Totally. Imagine just telling the AI what your specific character is doing and getting a perfect high quality image back.
The potential is huge. Game-changing, really.
And that's exactly what we're diving into today. We've been looking at some pretty fascinating research. Specifically, we're focusing on this new framework. It's called InstantCharacter.
Right, this comes from the teams over at Tencent Hunyuan and InstantX. They put out a paper detailing how they're trying to tackle these big challenges in personalizing AI characters.
Hmm. Yeah, you shared some great sources on the real cutting edge of AI image stuff. And this instant character paper really jumped out. It feels like a direct shot at those problems we've all faced getting consistent and controllable characters, especially with these newer, more powerful AI models.
Exactly. So our mission for this deep dive is pretty clear. Let's unpack how Instant Character actually works.
Yeah, what makes it different?
What are its main advantages, and why does the researchers think it's such a big step forward? Their goal, stated right in the paper, is high-fidelity, text-controllable, character-consistent images.
Okay, so before instant character, what were the main roadblocks? The paper talks about older approaches, right?
It does. It really highlights the limitations. First up, these tuning-based methods.
Tuning base, what was the main issue there?
Well, the core problem was needing to basically retrain or fine-tune the whole AI model for every single new character.
Wow, okay, that sounds intensive.
Hugely intensive. Think about the time, the computing power. But maybe even more importantly, all that heavy tuning could actually sort of mess with the model's general smarts.
How so?
It often reduced how well you could control the character or the scene using your text prompts. The fine-tuning made it too specific almost.
Ah, I see. So you might get a character that looks right, but telling it to, I don't know, ride a unicycle or sit under a tree,
Mm,
that might not work so well.
exactly. The text control just wasn't as reliable. It kind of degraded.
Okay, so that's tuning based. What came next?
Then you have the adapter-based methods. The idea was more efficient. Use smaller add-ons, the adapters, to inject the character features into a model that was already trained.
Sounds smarter, less brute force.
It was, but the paper points out a key issue. Most of these were built on older tech, specifically UNet architectures. Groundbreaking for their time, sure, but they have limits.
And what were those limits, especially for characters?
The big one was generalizability,
Mm.
handling what the paper calls open domain characters.
Open domain, meaning.
Basically, characters with all sorts of looks, different poses, various art styles,
Mm-hmm.
from super realistic people to like stylized anime figures.
Okay, so a wide range.
A huge range. These older adapter methods often struggle to capture the unique details across that variety, and they often produced images that just weren't as sharp or high quality compared to what newer models can do.
Right, so the fidelity wasn't quite there. You might get something like your character, but maybe blurry or it misses the specific style.
Precisely. The paper kind of contrasts them with the newer stuff, suggesting those older architectures just weren't really up to the task of diverse characters and high quality.
Okay. Now, the paper also mentioned something newer, diffusion transformers, or DITs.
Yes, these are a more recent type of image generation model, and they've shown, well, frankly, incredible potential for higher quality, more flexible image generation.
Hmm.
But interestingly, the researchers noted that people hadn't really dug into using these powerful DITs specifically for personalized characters. It's sort of an unexplored area.
Gotcha. So limitations with the old ways, untapped potential with the new DITs. That brings us back to instant character. How does it bridge that gap?
Okay, so Instant Character is built specifically on one of these newer Foundation Diffusion transformers.
Mm-hmm.
They mentioned the FLUX 1.0 dev model.
Right.
And the key thing is, it's designed right from the start to handle that wide character variety,
Hmm.
produce really high fidelity images, and crucially leverage the power of that DIT architecture.
And the paper highlights three core advantages, yeah. Let's start with the first one, generalizability. What does that actually mean in practice?
Generalizability here means it can handle a huge spectrum of character types, like really diverse, photorealistic people, anime characters, you name it.
Okay.
Figure 1 of the paper shows this off really well. You see examples like an anime character holding a sign, Some person chilling on a beach, another at a
I
piano.
remember seeing one that looked like Ultraman on a bike.
Yeah, exactly. That kind of diversity. And it does this while keeping the image quality high across different poses and styles. It's not just locked into one look.
That ability to handle diverse styles, think about game development or animation, that saves so much time compared to manually creating every single pose or variation.
Absolutely. Instead of endless manual iterations, you could potentially guide it with text, freeing up artists for more creative stuff.
Okay, so that's generalizability. Advantage number 2 is scalability. This sounds like it's about how it handles the character's specific features.
That's pretty much it. At the heart of this is what they call a scalable adapter. Now, think of an adapter like a translator.
Okay.
It takes the visual info from your character reference and translates it into a language the big, complex diffusion transformer can understand and use.
Makes sense.
This adapter uses layers of transformer encoders, basically, sophisticated processing units that are really good at pulling out and managing the key visual details that make a character unique.
And why scalable?
The scalable design lets it effectively handle those diverse open domain characters we talked about. It can adapt to simple or complex characters and interact smoothly with the DIT's internal understanding of images, what they call the latent space.
So it's not a rigid, fixed thing. It adjusts based on the character's complexity.
Exactly. It helps InstantCharacter find and use the right character features within the AI's, like vast visual library.
Okay, that makes sense. And the third advantage, versatility. This seems linked to the data they used for training.
Absolutely. You can't build something this flexible without the right data. They mentioned using a huge data set, around 10 million images, all focused on characters.
10 million.
Yeah, massive. But the really clever part is how the data is structured. It's not just one big pile. It's divided into paired and unpaired sets.
Paired and unpaired. What's the difference there and why does it matter?
Okay, so unpaired data is basically just images of characters, different views maybe, but without specific text saying what they're doing or where they are. Using this, the AI learns to just reconstruct the character accurately, focusing purely on getting the visual identity right, like teaching an artist to recognize someone from any angle.
Got it. Learning who the character is.
Exactly. Then you have paired data. That's character images plus text prompts describing actions, scenes, poses.
Ah, so that teaches it the what and where.
Precisely. It teaches the AI how to generate that same character, the one it now recognizes, doing new things based on text commands. This dual approach is super important. It lets the model learn identity consistency and text control separately, kind of, so the two goals don't conflict.
That's smart. One data type nails the who, the other nails the what. Okay, let's dig back into that scalable adapter for a second. How does it actually pull out the character features?
So it starts with these things called general vision encoders. They mention using SIGLIP and DNOV2. These are powerful AI models already trained to understand images really well.
Like off-the-shelf image understanding tools.
Kind of, yeah. Pre-trained. Interestingly, they chose SIGLIP over CLAP, which is maybe more common, because SIGLIP is apparently better at grabbing the really fine details.
Which you definitely need for unique characters.
Crucial. And they add DynoV2 to help it ignore distracting backgrounds, making the feature extraction more robust.
Yeah.
They combine info from both to get a solid initial read on the character.
Okay, so that's the first pass. But then there are intermediate encoders and this dual stream feature fusion. Sounds complicated.
It's a bit technical, yeah, but the core idea is pretty neat. They want to capture both the tiny, fine-grained details and the broader shapes or features of the character, especially for high-res images.
Because the first encoders might miss some stuff.
Right, they operate at a slightly lower resolution.
Yeah.
So this dual stream thing happens. One stream focuses on low-level stuff from early in the vision encoders catching fine details.
Okay.
The other stream divides the reference image into regions and analyzes those to get the features at a regional level. Think like understanding the arm shape versus just the texture of the sleeve.
Ah, details in bigger picture.
Exactly. These two streams get processed separately by intermediate transformers and then combined, fused together. This gives a much richer, more complete character representation.
That is clever. It's like zooming in and zooming out at the same time. And then there's a projection head and a time-step-aware cue former. What's their job?
Okay, the projection head is the final step before handing things off to the image generator. It translates that rich character info into a format that Diffusion Transformer understands during its creation process, that step-by-step denoising thing.
Right, where it goes from noise to image.
Exactly. The cue former is a special part that helps refine these features and makes them aware of the time step. Think of it like The AI needs slightly different character guidance early in the generation versus later when it's refining details.
So it adapts the character information based on how finished the image is.
Sort of, yeah. It ensures the guidance is relevant for that specific stage. And finally, these processed features get fed into the main DIT using something called cross-attention. That basically tells the DIT, hey, pay attention to this character detail when you're working on this part of the image.
Okay, that gives a much clearer picture of the adapter. Now, the training. They use a three-stage strategy. Why break it down like that?
That three-stage approach is really key. It's about carefully balancing those goals we keep talking about: character consistency, text control, and image quality. Sometimes these goals can pull in different directions.
So sad.
Well, if you push too hard on text control early on, you might lose character consistency, or vice versa.
Oh,
Breaking it down lets them focus the learning.
makes sense. So stage one, unpaired beta, lower resolution. What's the goal?
Stage one is purely about locking down that character consistency. Using unpaired images, just different views of the character, no action prompts, lets the AI focus entirely on learning the core visual identity.
Nailing the who.
Exactly. Learn to reconstruct the character accurately from different angles, get that identity solid first. They found doing this at 512 pixels was way more efficient to start.
Okay, build the foundation. Then stage two, still 512 pixels, but now using paired data. What changes?
Now the focus shifts completely to text controllability. The model knows the character's look, right? So now it learns to generate that same character doing different things in new poses, new scenes, based on text descriptions.
Preventing the copy-paste look.
Precisely, making the character actually integrate with the scene and follow instructions, not just get slapped onto a background. Figure 6 in the paper shows this really well. Same character, different actions, different places, all from text.
Right, so it learns to perform. And then stage three, the final stage. Higher resolution, both data types.
Stage 3 is all about the polish, upping the visual quality, the details, the textures, getting those high-fidelity results. They bring in high-res images, both paired and unpaired, and fine-tune the model.
To make it look really good.
Exactly. Visually impressive, detailed, but still consistent and text controllable. They found even a short period of high-res training here made a big difference.
It sounds like a really logical progression. Build identity, add control, then enhance quality. Very methodical.
It seems very well thought out, yeah. Avoiding those conflicts between different objectives.
Now, the proof is in the pudding, right? The paper compares InstantCharacter to other methods. What did they find?
Yeah, the comparisons are pretty interesting. You can see them in figures 3, 4, and 5. They tested it against some big names: a mini control, easy control, ACE, plus R, ILD, even GPT-4o.
Wow, GPT-4o as well. That's a high bar.
It is. And the results, well, they suggest InstantCharacter performs really strongly. The analysis shows that while other methods have strengths, they often struggle with balancing everything.
Like, what specific weaknesses did they point out?
Well, for example, a mini control and easy control apparently had trouble keeping the character looking consistent. The image might match the text prompt's action, but the person just wouldn't look like the reference anymore.
Okay, so losing identity.
Yeah. ACA++ was okay on simple stuff, but struggled with complex actions in the prompts. And interestingly, sometimes went the other way. It was too rigid in keeping the character look.
Rigid, meaning?
Meaning it wasn't great at changing the pose or background significantly based on the text because it was so focused on preserving that initial look. Not enough editability.
I see. And InstantCharacter versus GPT-4.
It held its own, apparently achieving comparable results in many cases, which is impressive given GPT-4 is this huge, closed model. But InstantCharacter seemed to consistently nail the combination, preserving detail, high fidelity, and accurate text control, even with tricky prompts.
That's a strong showing. And it wasn't just basic generation, right? There was something about style transfer.
Yes, that's in Figure 5. Another really cool capability, InstantCharacter can work with style lorries.
Lorries, those are like style plugins.
Pretty much, yeah. Small models fine-tuned for a specific artistic style. InstantCharacter can apply these styles. They show examples like Ghibli or Makoto Shinkai styles without messing up the character's identity or the text control.
So you get your character doing what you asked, but drawn like it's from a Ghibli film.
Exactly. And the paper notes that other methods they looked at, like Gemang or even GPT-4, didn't handle that style transfer quite as flexibly.
That feels like a massive plus for creative work. Okay, so let's wrap this up. What are the main takeaways from this InstantCharacter deep dive?
I think the big takeaway is that this really does feel like a significant step forward for personalized character generation. Using those diffusion transformers, the smart adapter design, that careful training strategy,
Mm-hmm.
it genuinely seems to overcome a lot of the old hurdles.
Yeah.
It could really help with bottlenecks and things like character design for games or animation,
Yeah.
making larger projects with many unique characters much more practical.
And for you, the listener, tuning in because you're interested in AI image creation, what does this mean for you?
Well, it points towards a future where you can create virtual characters that look better, higher fidelity, where you have much finer control over what they do and how they look just using text.
And it works for a wider range of characters, too.
Exactly. Photo, cartoon, whatever.
Mm-hmm.
It really brings that idea of easy, consistent, controllable character creation much closer for, well, potentially everyone.
So here's something to think about. What happens when this tech gets even better, even more accessible? What does it mean for creative fields? Sure, but also for things like virtual identities, digital avatars. How might we interact with AI differently?
Yeah, what new kinds of stories, what new art forms could this unlock? It's fascinating to consider.
Definitely. And if you want to dig deeper yourself, the researchers actually made the source code available on GitHub. We'll make sure there's a link in the show notes along with a link to the paper itself. Definitely worth exploring.